the structure, the mathematical structure of the equation, these are called parameters. So when you hear people talking about model parameters, parameters are coefficients that are introduced in model equations that typically cannot be measured and are introduced to take into account processes that we cannot quantify through measurements. They give flexibility, but don't change the model structure. Okay, so we know what are parameters, we know what are constitutive equations, we know what are parameters. And of course, these parameters that cannot be measured in some way must be estimated. So you understand that there is a problem here. Okay, but let me go back to the discussion of the energy equation. And let's look at this rational formula, rational method, and how to put here the right I. Rainfall intensity is something that varies in time, varies depending on location. What is the right intensity to be plugged into this equation? First, note that rainfall intensity depends on the duration of the event. I already discussed this. Long event, low intensity, short event, high intensity. So, rainfall intensity depends on the duration. Also, it depends on what is called the return period. I think you already know what is a return period. Can you please raise your hand if you know what is return period? Everybody, almost everybody, okay. Return period is, you know, I don't give you the full definition for now, and maybe I'll give you later, but return period of a flood, you have an intuition of what it means. Okay, when I say a flood with a return period of 100 years, more or less you think that this flood happens on average every 100 years. Okay. So, when I put here an extreme rainfall, I have to decide duration and return period. So, the return period is easily solved. Typically, if I want to estimate a river flow, a peak flow with a 100-year return period, I put here a 100-year rainfall. This is another assumption, which is not true, but anyway, it's an assumption, and I don't want to discuss it. But the duration of the event, I want to discuss this. So, what is the duration of the event that I have to use to estimate this rainfall intensity? There is a proof, a mathematical proof that proves that, again, under certain assumptions, the duration of the event that I have to plug here is the concentration time of the catchment. Okay, what is the concentration time? Let's suppose that I have a catchment, and please learn this. I'm not sure it is somewhere in my web pages, but it's something that a person studying water resources management should know. So let's suppose that you have a catchment. I'm sorry, the blackboard is small here, but okay, let me work here. So let's suppose that we have a catchment with a river collecting water, and let's suppose that it rains over the catchment. So you have a uniform rain, let's call it, it's I. You have a uniform rain over the catchment, and let's suppose that we can estimate the time that is taken by each single drop to reach the closure of the catchment, the river cross-section of interest. And for each single drop I can estimate the time, and there is the longest time, of course, and the longest time taken by the furthest, I'm not sure if my pronunciation is correct, furthest drop, it's the concentration time. Okay, so there is a mathematical proof that proves that the highest flow is given if I plug in here the rainfall intensity that corresponds to the concentration time. but the concentration time, it's related to velocity, to the time taken by water to get to the closure, and velocity is related to energy. So if the catchment is steep, this means that the flow is faster because there is more energy, because there is more potential energy. Because rainfall, when it falls over the ground, it takes a potential energy. And the potential energy is related to the altitude. So a catchment that is steep will have a short concentration time because there is more energy in water. If the catchment is flat, there is low energy in the water, which translates in a longer concentration time. So basically this proof that I mentioned to you, that tells me that I have to put the rainfall with the concentration time there, with duration equal to the concentration time, implicitly takes into account that the higher the energy of the catchment, the lower the concentration time, the shorter the duration of the critical event of rainfall. So implicitly there is conservation of energy. And keep in mind, there must be, it would be impossible that in some corner of this equation there is no conservation of energy, because this equation is describing a process that results from conservation of mass and conservation of energy. So if you see an empirical equation that describes a physical law, describes the movement of a body in this case, you should ask yourself, where is conservation of mass, where is conservation of energy? And what I just told you is something that I elaborated, because I started from this very reasoning. I said, okay, conservation of mass is clear in the rational method, but where is conservation of energy? And I thought there must be in some way. And this is the reasoning that I elaborated. Of course, you can feel free to disagree. And this is written in my web pages. I didn't write it, it was elaborated by me, of course. But this is something that, in some way, you should elaborate. And, you know, it helps a lot, your activity, if you try to understand what's going on. If you try to really get a perception of the process that you are describing, and this translates in your experience. When one says, ah, this is an experienced engineer, one associates experience to age. Absolutely. Experience is to be associated to understanding. And this gives to you more sensitivity. You look at a catchment, you understand a lot of energy, infiltration very reduced because you see a lot of rocks, and then you elaborate already an idea on how the catchment works. Okay, I think we can continue on Monday, and then on Thursday you bring please your PC and we make exercises. Good.